It is my great privilege. I am thankful to the organizer for the same. I'll be talking on a theorem on the generic form of the quantum cluster integral. The topic is very simple. I hope I can finish ahead of time. My collaborators are here, Shomi De, Pratush Manchala, Srijit Basu, and Devshikha Banerjee. Most of them were MSc students at the University of Hyderabad. Now they are pursuing PhD in various places. Plan of my talk is as follows. I'll first introduce the cluster expansion for an interacting classical gas. Then I'll come to quantum cluster expansion for a free Bosch or Fermi gas. Then I'll come to quantum cluster integral for a Bosch or Fermi gas in any restricted geometry. Then I'll come to our theorem on the generic form of the cluster integral. Then finally I'll conclude. The Mayer cluster expansion of the grand free energy for an interacting classical gas takes this form. So here P is pressure and V is volume. So I wrote everything in usual notation. So this Z is the fugacity, and H nu is the new cluster integral for a cluster of new particles in the gas. So for such a system, we have the following results. So H1 equal to V by lambda T cube. So this is nothing but the partition function for a free particle in 3D. H2 takes this form. So in H2, interacting potential is involved. So lambda T is the thermal de Broglie wavelength, and this Z is the fugacity I already told. So natural question comes, what would be the cluster expansion for a quantum gas in a harmonic trap, which drew enormous interest in the last 2.5 decades in connection with the ultra cold atoms. So though the cluster integrals are different for different systems, the form of the classical cluster expansion does not change even for an ideal quantum gas. The generic form of the quantum cluster expansion for an ideal Bosch or Fermi gas takes the form. So it takes the same form. So where the quantum cluster integrals take this form. So yeah, so this H nu is different in classical gas, and for a quantum ideal gas, this H nu takes this form, where this rho Ri Rj beta. So this is an element of the unnormalized density matrix. So e to the power minus beta h is the unnormalized density matrix. So this is an element of the unnormalized density matrix for a single particle of the quantum gas. So this form, though was initially proposed for free Bosch or Fermi gas, it remains unaltered even for any trapped ideal quantum gas. The new quantum cluster integral H nu for the ideal quantum gas arises purely from the exchange effect with cyclic permutation within the cluster of new particles in the system. Evaluation of the quantum cluster integral seems difficult because the individual density matrix elements in H nu are not independent. So here R2 is here, R2 is here also. Because of this, this integral seems difficult. And before us, nobody could obtain a generic form of the cluster integral. So we can overcome this difficulty by applying our theorem where completeness of the position states plays a significant role. So H nu is here. So these are the density matrix elements, and these elements can be written in terms of position states and bras, and also the density unnormalized density matrix. So now here we see here is R j minus 1 ket, and here here rj minus 1 bra, and we are integrating over rj minus 1. So if we do this, we will get 1. So that way we can do this for all the variables except for r1. So eventually we end up with uh, um, trace of a trace of rho to the power nu. Okay, so now this trace of rho to the power nu is trace of e to the power nu beta h, because rho is e to the power minus beta h. So only nu will appear over here. So now this trace can be written in terms of the energy eigenvalues. So here Ej1, Ej2, Ej3 is the energy eigenvalue in the single particle state, psi J1, J2, J3, and the summation over J1, J2, J3 are taken over complete and orthonormal set of the single particle states. Hence, we obtain quantum cluster integral for the cycle of length nu as this. So this can be written. So this is nothing but the partition function for a single particle, where the beta is replaced by nu beta. So this is the generic form of the cluster integral. So since this appears as partition function for a single particle, um, with beta replaced by nu beta, we interpret it in different way. So Z nu beta is the canonical partition function for a composite particle composed of nu indistinguishable constituent particles in the cluster of size nu at the temperature T equal to 1 by kb beta. It is to be noted that the energy is an extensive variable, at least for the ideal gas of particles. So the energy of the composite particle in a given energy eigenstate psi J1, J2, J3 is nu times the energy of the constituent particle in the same eigenstate in the cluster of size nu. So this is our result for the generic form of the cluster integral. So it's actually very easy. So evaluation of partition function for a single particle is very easy. So once we can do this, then we can simply multiply it with number nu. Then we can say, so this would be the partition function for a cluster of size nu. Yeah. So let us come to our theorem now. The generic form of the quantum cluster integral for a cluster of size nu of any system of ideal indistinguishable bosons or fermions in the thermodynamic equilibrium would be plus minus 1 to the power nu times the canonical partition function of a single composite particle composed of nu bosons or fermions in the cluster. So this theorem was published in Physica Scripta. So using this theorem, we obtain quantum cluster expansion of the grand free energy in a closed form for an ideal Bohr-Fermi gas in both 3D box geometry and the harmonically trapped geometry. So our theorem for the quantum cluster integral is generic for ideal quantum gas. It could be any free gas or any trapped gas in thermodynamic equilibrium. No approximations are involved in our proof. Hence, our theorem can be useful to capture finite size effect on any quantum gas. So, let me thank the organizers again. I would also like to acknowledge ACRB for partial financial support, and finally, thanks to all of you for your kind attention.
So any more questions? Any questions? So if no more questions are there, let's thank the speaker.